Good morning. My name is Joseph, and I'm a PhD student at the University of Virginia. Thank you for having me to present our work on AI-assisted framework for microstructural design for targeted property. Before we begin, I would like to acknowledge our teammates. This work has been prepared in collaboration with Dr. Beck's research group from the University of Virginia and Dr. Uday Kumar's research group at the University of Iowa. I'm sure you're all familiar with this, but I would like to share a quick introduction to our problem. The energetic materials are key components in many systems and applications, not only in propellant and munition systems, but also in mining and other civilian applications. The sensitivity of the high explosives is critical as it correlates to performance and safety directly. As we all know, the high explosives have a strong structure property performance SPP relationship where the microstructure highly affects the sensitivity of the energetic material. For example, given two different microstructures in different crystal sizes, we can observe how different the temperature evolves under the shock loading over the time. Traditionally, to design a new microstructure, we first determine the target property. Then we design and create a sample led by our experience, knowledge, and intuition. Then the candidate design is validated through the direct numerical simulation or physical experiments. This loop continues until we are satisfied with the candidate design and its property. I believe we may all have come across that this process being very slow and expensive, as it takes multiple of hours and days to evaluate a single case of the microstructure. And then the design search space is very vast, as there can be more than thousands of microstructural designs we can prepare. And microstructure representation is limited to only idealized shapes using geometric primitives, such as polygons and ellipsoids, and simple shape descriptors, such as void or crystal sizes, aspect ratio, and orientations that are not able to model all complex microstructure details, such as elongated voids. Thus, it's practically impossible to fully explore the design space and converge on an optimal solution. Our proposed framework brings AI assistance to better represent microstructure, rapidly estimate the property and performance, and efficiently optimize the vast search space by minimizing the number of expensive experiments while still finding a microstructural design for the targeted property. The first AI assistant enhances microstructure representation to model all possible shapes and configurations. And it also provides better controllability that allows a more sophisticated optimization process. We employed Generative Adversarial Network called GAN, which is a deep learning method for the generative task. GAN contains two neural networks called the generator and discriminator, and they compete each other during the learning process. The generator learns the underlying distribution of microstructure by creating realistic microstructure, and the discriminator learns to distinguish whether the given microstructure is real or fake. Towards the end of the training, the generator reaches the ideal level of performance where the discriminator cannot distinguish whether the generated image is real or fake anymore. What really attracts the GAN method the most comes from its strong parameterization that describes microstructure with a low dimensional latent vector. The generator creates a synthetic microstructure from a latent vector. During the learning process, the generator learns a mapping from the latent vector to a unique microstructure. As a result, the latent vector serves as a latent code to uniquely represent a microstructure. We can tweak the values of the latent code to generate and represent unique microstructure. To better visualize how it works, in an analogy, we have 15 knobs that we can turn and tune for a specific value ranging from -1 to +1. And we can basically turn these knobs to create different latent codes for different microstructures. Another beauty of the GAN method is its controllability, which would allow sophisticated optimization. For example, we have two microstructures in the latent space. We can navigate from one code to another by turning the knobs, and we can observe a very smooth transition of synthetic microstructure between the two. More details of our work on GAN can be found in the reference. Although we have a search space defined and we can navigate around, it is still impractical as each evaluation through DNS is too time-consuming and costly. Thus, we bring the next AI assistant to estimate the property rapidly and accurately, where it takes less than 0.5 seconds for each evaluation. Previously, we developed a neural network model called PARC for rapid estimation of the SPP linkage. The exciting part of the PARC model comes from its interpretability. Conventional deep learning models would simply describe and predict the input and output relationships and stays as a black box model, but PARC was carefully designed to model differential equations of thermodynamics of the energetic materials. And as a result, instead of predicting the property and performance directly given an input, this PARC predicts the evolution of the temperature and pressure to better understand what's going on in the black box model. Thus, the property and performance are calculated from those estimated states. In a nutshell, PARC takes microstructure image as an input, extracts the shape information, and then the differential approximator and integration approximator are modeled in the language of neural networks to predict the evolution of temperatures and pressures over the time. You can find more details on our work for the PARC in the reference. Here we show the performance of the PARC. We can observe the evolution of the temperature of the ground truth, and then the prediction from the PARC. It is not perfect, but can still predict the evolution of the temperature quite well, but its estimation of the property lies in good agreement with the ground truth, which is the true interest. Since PARC is only an approximation model, not a simulation, the prediction is not perfect. But considering its compatibility to DNS in terms of the amount of time required, over 24 hours versus 0.5 seconds, the PARC model has a lot of room for potential in optimizing material design for targeted property. Thus, we have a stage set for optimization with the search space defined by GAN and with the expedited evaluation using PARC. Now we need an optimizer that connects the GAN and PARC together to suggest a microstructural design for the targeted property. We employed a gradient-free optimization for the following reasons. Because an objective function of the latent search space is very complex and expensive, because we need an efficient optimization method as the search space is very vast, as it would require over 10 to the 16 evaluations for a grid search method. Also, we need an optimization method with uncertainty because we have a very limited number of labeled data where the deep learning methods are prone to overfit to the training data and the performance varies if a microstructure is much different from the samples of the training data set. To have an uncertainty quantification in estimation, we expanded PARC into Bayesian formulation by applying Monte Carlo dropout by Gale. Please find more details of those methods in the reference. The optimization method works as follows. The population of microstructure is randomly generated in the search space. Each of the microstructure creates a variant microstructure by taking weighted vector differences using other microstructures in the population. Then the PARC comes into play and rapidly estimates the property of the target and variant, then determine whether to update the population or not by comparing their estimated property. For example, if we are optimizing for the more sensitive microstructure, we will not update the population for this variant. As mentioned previously, we extended this gradient-free optimization to concern uncertainty in estimation. To do so, we utilize a method called expected improvement, which was first suggested by Jones in 1998. The expected improvement has two major terms called exploration, and exploitations. In the case of optimizing for high-sensitive microstructure, the exploration strives to suggest the most sensitive microstructure from the current knowledge, but exploration strives to improve the knowledge by exploring the uncertain regions in the search space. Thus, the expected improvement measures the likelihood of observing more reactive microstructure by balancing the information from this exploitation and exploration well. With this optimization process, we drive the population of microstructure into the high regions in the search space, then suggest the candidate microstructure with the highest expected improvement as a result. In order to validate our suggested framework, we optimized microstructural design of HMX, which is high explosive known for strong SPP linkage, for the maximal reaction rate as a targeted property. We started with 42 labeled cases of HMX with the most reactive microstructure having 28.23 micrometer square per nanosecond. Using our suggested framework, we found a new microstructural design over 180% increasement compared to initially best known through only a few design iterations. Furthermore, we observed that voids mostly aligned parallel to the direction of the shock propagation are highly reactive, which corresponds to the results shared by Wright et al. In 2017. In conclusion, we suggested an AI-assisted framework for microstructural design with targeted property by introducing a GAN for better microstructure representation and introducing Bayesian PARC for accurate and rapid estimation, and efficient optimizer that produces a near optimal solution. And we validated our suggested framework by discovering a new design with over 180% increasement in reaction rate. This work is an ongoing project, and we want to expand our framework by including constraints to optimize for specific property value other than just an extreme property. And also we plan to expand the framework for other design parameters, such as different initial shock pressures. Thank you.